Today we're going to be talking about gravity. What is gravity? And I always do an experiment. You saw it here for the first time ever. Okay, nobody else on planet Earth has ever done this experiment. Very expensive. Okay, we take a pencil. Okay, watch carefully because this is astounding. And you let go of it, and it falls to the floor, to the table in this case. And just in case, I'll do it repeatable because it's got to be repeatable in mathematics for it to be scientific. So we let go of it. Here it goes. There you go. See? You let go of it, falls to the floor. Never has it fallen to the ceiling whenever I do it. Okay? And so the question is, what brings it down? Why does it come down? What causes it? What's the mechanism? Okay? What comes in contact with the pencil? What physical object called? I mean, I'm holding it. So when I hold it with my fingers, yeah, it stays there. But as soon as I let go of it, it comes down. No way you can stop it. And so the question is, why does it go up? I mean, I want it to go up sometime, and it doesn't. Never been able to do that magic trick. Okay. So what's the deal? Well, here's a couple people. Several really. I've got 3 cases here where people have shown that when you drop it, it falls to the ground, but then you have, this inertia, this resistance that we talked about a minute ago, okay? Like the air, if you take a feather and you let go and, it doesn't fall like a stone does. It kind of floats there. Why? Because it's got this resistance. There's inertia, I guess, right? A little bit of inertia, a little bit of resistance, okay? And so the feather doesn't fall at the same rate, at the same acceleration as a stone. And here you have one fellow, his name is Brian Greene, and he went to a special place to do this experiment. They dropped a feather and a ball, and they both fell at the same time. Why? Because that chamber, they removed all the air. Okay, and so you can see there's no resistance, and it's uncanny. It's really unbelievable that a feather would fall at the same rate as anything else instead of floating. And all they did was remove the air. And here's another example of that. Okay, a fellow did the same thing. He had 2 boxes. In one he removed the air, in other ones he left it. And you can see the one with air, what the feather does. It kind of drifts because it's got all this resistance with the air, and the other one where there's no air just falls at the same rate as the little metal piece there, okay? And just in case, for those of you who are not flat earthers, we did it on the moon as well. An astronaut dropped a feather and a hammer, and you can see that they fall at the same time, okay? So he did it as careful as he could, okay? And there it is. No air on the moon. Okay, so he proved that there's no air on the moon, right? And without that resistance, the feather falls at the same rate as the hammer. Okay, so we call that phenomena gravity. They both fall down. You can see that even on the moon, for those of you who are not flat earthers, the hammer and the feather did not go out into space. They both fell to the center of the moon in that direction, right? Okay. Because the moon is round. Again, not for flat earthers. Flat earthers think the moon is flat, I guess, right? Okay, so what is this gravity thingy that pulls it down? Here's a definition. Okay, one's from dictionary.com, the other one from Wikipedia, and one says, gravity, the force of attraction by which terrestrial bodies tend to fall toward the center of the earth. Okay, that's the notion. What is it? It's a force of attraction, essentially, right? And Wikipedia says a fundamental interaction which causes mutual attraction between all things with mass or energy. Okay, so you have a mutual attraction and you have the force of attraction or fundamental interaction, right? The question is, you have an attraction. So gravity is not repulsive, okay? So whatever you let go of, it falls to the ground unless there is some resistance. And then we have to go into inertia. But if there is no resistance, it'll just, or the resistance is irrelevant, like in the case of a stone, then the thing will fall at the rate that it should be falling, which is 9.8 meters per second squared. That's the acceleration of gravity here on Earth, and that's how fast, or how, the acceleration of gravity here. That's how you can expect the thing to fall to the ground at that rate. Okay, so gravity is some kind of force. That's a concept. So far we haven't said what gravity is. All we're saying is, look, we're going to call that phenomena gravity. Okay, and what is gravity? Gravity means that something falls to the floor. Essentially, there's a attraction. There's what is it? You could say it's attracted by the Earth somehow. Okay, magically, whatever, but it's attracted. And here's NASA. Okay, this is their version. It says gravity is a force. Okay, and again goes the same thing as the other two. And it says, why do you land on the ground when you jump up instead of floating off into space? Yeah, why? And it says, why do things fall down when you throw them up or drop them? Okay, why? Yeah, I want to know why. The answer is gravity. Gravity is just a name. You could have said the answer is intelligence. The answer is love. I mean, love is attractive, usually, right? So, okay, so it's love. And what do you mean by that? I mean, did love cause, we're talking physics here, right? Did love bring it down? What's the physical mechanism? And, of course, no one even remotely has any idea. Okay, all these mathematicians, they never discovered that. Here we are 2,000 plus years later, since the Greeks dealt with some of these issues. Nobody has figured it out there in mathematical physics. Okay? We have, but not them. Okay, so here we have a fellow jumping on the moon, on the Earth. Okay, and you can see he tries to jump, but he doesn't go out into space. He falls back to Earth. Okay, and so what they've concocted is they said, well, the ether maybe, or who knows what, and we have all these particles, right? And they think it's a question of particles. Okay, and so they try to explain it with particles, but see, the problem is with particles coming out of objects such as atoms, right? They can only go one way. So assuming, there are particles coming out of your body, out of every atom in your body, right? Photons, for example, right? And then you have all these particles, we'll assume that they exist, right? And all these particles are coming from every direction. They're coming even from the atoms on the Earth. So why would you fall towards the center of the Earth? Why not? I mean, if you're in the middle of all these particles coming from every direction, you shouldn't move anywhere. Okay? If you jump, you should stay up in the air. Why do you come down? You can't explain it with particles. And someone who simulated these things with particles was Newton, but he gave up. He wrote a couple things that we have from him today. One is a letter to Richard Bentley, and he says that gravity should be essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has competent faculty of thinking can ever fall into it. Okay? And so he says gravity must be caused by an agent. Yeah. And then in his book he says, I do not feign hypothesis. Okay, he had no idea, but he simulated everything with particles because he had no other idea what to simulate that with. Okay, but he was under the idea that, gravity must be caused by an agent. But it turns out that he can't see or touch whatever this agent is. Things simply fall to the floor, and I can't see or touch what's pushing or pulling them downwards. Okay, so he finally gave up. He says, I feign no hypothesis. Okay, but he did everything with particles. He was a particle man, corpuscles. Okay. So today, the people in quantum mechanics, they haven't given up on particles because their religion is a quantum based on the quantum, on the particle. Okay, particle that ain't a particle, by the way. It's an amount, quantity. It's a number. But they treat it as a ball, okay, whenever they want to give their physical interpretation. Okay, and so here you have a couple instances. Okay, here's quantum attraction. Um, they call it transfer of negative momentum. And here's just an example of a quark shooting a gluon outwards and somehow drawing another quark inwards, you know? And here you have another fellow, and his name is John Baez, Juanito Baez, I call him. Says, if I throw a ball at you, the recoil pushes me back. He says, the answer, and he's trying to explain, he says, the answer lies in the Heisenberg's uncertainty principle. The photon can be created by one particle and absorbed by the other. If the momentum transferred by the wave points in the direction from the receiving particle to the emitting one, the effect is that of an attractive force. Here it goes again, just in case. If I throw a ball at you, the recoil pushes me back. When you catch the ball, you are pushed away from me. How can this attract us to each other? Yeah, good question. The answer lies in the Heisenberg's uncertainty principle. The photon can be created by one particle and absorbed by the other. Okay, so that's what he's saying. It's absorbed. If the moment transferred by the wave points in the direction from the receiving particle to the emitting one, the effect is an attractive force. Okay, so you can see how they're doing all this magic. They can do it mathematically. They say, yeah, we just change the sign or whatever. And yeah, that's great. That's got nothing to do with physics. Show me in a lab how you can do that. Okay, you like experiments? There, that's where you have to do experiments. Just show me an experiment where you show gravity, right, with negative momentum. Okay, just simulate, throw a tennis ball at something and attract it. Okay, and here's another fella. His name is Victor Stenger. And give me a second here so we get to the beginning. The vacuum is capable of producing interactions between particles at effective space-like separation. This occurs when quantum fluctuations in the vacuum cause a particle to zigzag. Let me explain. No doubt the idea of motion backward in time makes a grievous assault on common sense. Yeah. However, to a particle physicist raised on a diet of Feynman diagrams, motion backward in time is not all that disturbing. All fundamental particle interactions work backward as well as forward. And so these people believe that they can get away with saying, look, we just changed time. We put a negative sign in front of the little t, and we've got it made. Okay? So these folks are really saying that, you know, they can produce attraction by throwing something outwards one way. Okay? They have no problem believing this. And the question is, how do they justify it rationally? And they can't. They just say, you know, again, like this fellow says, you can't even imagine that. How do you throw the ball and attract? And so they had to create negative momentum transfer. And that answered, I guess, Newton's concern. You know, how do you produce attraction with particles? And these people said, we can do it. We just caught negative momentum transfer. We transfer attraction. Okay. Okay, so what is that particle called? It's called the graviton. Okay, and what is a graviton? Well, here you have an idea. It says the graviton is the hypothetical quantum of gravity, an elementary particle that mediates the force of gravitational interaction. This is all out of the Wikipedia. There is no complete quantum field theory of gravitons due to an outstanding mathematical problem with renormalization in general relativity. Okay, in string theory, okay, so they moved from quantum to string theory now, which is a variation on quantum. That's all it is. One of the vibrational states of the string gives rise to the graviton. Okay, so they're just saying that it's a little string that's vibrating. It's more like you know, like this. More like something like this, and they move it around in different directions. They say, well, that's a particle. Okay, great. And so it says, one vibrational states of the string gives the rise to graviton, a quantum mechanical particle that carries gravitational force, carries it on the back, okay? They always talk about carrying force, carrying interactions. How you do that, I don't know. And we don't carry concepts in science. The string theory is a theory of quantum gravity. Okay, you got that? It's a theory of quantum gravity. In string theory, the graviton is a massless state of a fundamental string. If a massless spin 2 particle is discovered, it must be the graviton. So here you have a picture of that, okay? This is what a graviton looks like, okay? So if you see something like that around your house, floating around, hey, call the people at CERN, SLAC, Fermilab, you know, any of those. Brookhaven, National Laboratories, any of those. Tell them that you've seen a graviton, okay? It looks something like that. So now you know what it looks like, no excuses, okay? Okay, so if you see something floating like that, it's not a unidentified flying object, it's a graviton, okay? Okay, so here we have one fellow. His name is Matt Dowd. He's got, again, he's sponsored by PBS. I call it BS more than PBS, okay? And this is what he says. He says, dozens of these cosmic strings in a network across the universe. Okay, so all these strings somehow open up, they break, and then they weld together or sew together. He doesn't explain the process. He doesn't explain how that happens. They just do it. They just describe and illustrate that the string, this closed loop string, this closed loop rubber band or string or whatever, it breaks, forms welds or whatever with other strings, and then they form these loops again, then they break again, and they do all this stuff, and nobody tells us how that happens, okay? And what Matt does, he goes in there and he says the following. He says, a pair of kinks in the string are whipped back and forth by the oscillating string, okay? We see it there, okay? And the incredible mass in these kinks, they have incredible mass, okay? No, I don't know how they justify that. They just say it does. Causes them to radiate gravitational waves. And so they slowly decay away. Gravitational waves. I guess he's talking about space-time, right? These waves are going to travel through space-time because these massive strings, they vibrate and all these waves come out of there. Fine, no problem. How does that wave that comes towards me attract me? That's what I want them to tell me. Because a wave, like a particle, is a one-way mechanism. It goes outwards and does not come in. Okay, so we have a problem because these people do not explain the mechanism. All they say, look, it does so. Okay, so the wave comes out of the string, the closed loop string. It vibrates, creates waves in space-time, I guess, goes outwards, no problem. And here I'm on the receiving end. So we have waves coming towards me, like, in the ocean, when the waves come towards you. Well, the wave is not pulling you in, it's pushing you out. You could say that, later on, it pulls you inwards, okay? But that's not what these people are saying. These people are not saying, besides it's not going to pull you all, even if you're pulled by the wave, you're not going to be dragged all the way to the black hole. Okay, so what is the pull mechanism? Because, again, gravity is an attractive force. Explain attraction with this wave or your particles, either way. Okay? And that's where they can't. They don't have that. Okay, but it says that the string disappears. Disappears into what? It becomes part of space-time. I mean, here you have this string, right? This thing, right? It's vibrating. It sends waves out. And because it loses all this energy in the waving motion, this disappears. Where does it go? I mean, does it melt away? Does it become part of space-time? Was it a thing to begin with? I mean, is it a wave? What is this one-dimensional string? I mean, I don't know anything that's one-dimensional. I mean, what does one-dimensional look like? And they say it only has length. So, well, draw it for me. Draw your one-dimensional length, okay? And fortunately, someone here, his name is Brian Cox, he tells us where these gravitons go, why they disappear, why we can't see them. Okay, this is important here, so pay attention. And he says the following, he says that it goes to hidden dementia. Okay, you have dimension is one, dementia I guess is many, right? The reason gravitons disappear is that they vanish into a place beyond our reality, into some sort of extra dimension. Okay, great. How many drinks did you have? There can be extra hidden unseen dimensions. Okay, great. It sounds ridiculous. Absolutely. That's why I asked how many drinks you had. Bartender, I want whatever he had. And it is impossible to picture, but theoretically it's possible. I mean, these people are so gullible they believe anything that their teachers tell them, and they just memorize it for the test and then spread it out among humanity, right? And it's also possible that gravitons, the particles of gravity, can spend most of their time in those extra dimensions. So, yeah, if you're looking for a graviton, go to the other dimension, you'll find it there. Okay, that's what they're saying. They're hiding in the extra dimension. Okay, and so that's the quantum string version, right? Here you have Einstein's version. We covered that the other day. It's very simple, so we don't need to spend more time on this. The Earth doesn't fly out of the solar system because there's this canvas known as warp time. Okay, we have the seconds and the minutes, which are warped, or the years maybe, right? And they're warped, and they come up against the skin of our planet and prevent our planet from flying out of the solar system. That's what keeps our ball rolling around the sun. Okay, and so what can I say? These are the versions that you get. These are the explanations, the mechanisms that they offer you in mathematical physics. And so if you believe any of them, well, I don't know. I think you need to see a doctor, called a shrink. Okay? Well, how do we explain it? Well, obviously we explain it very simple because it is very simple. All we needed to do here, okay, when we had the pencil, right? All we needed to do here is figure out what invisible thing, object, entity, whatever you want to call it, body, is here or here. Something that comes in contact with a pencil. If it comes in contact with a pencil, we can explain why it falls, because there is no action at a distance. There is something in contact with a pencil. Physical contact with a pencil other than the air, right? There's something invisible, intangible, that's coming in contact with a pencil. Okay? If you say there ain't, you say that there is nothing that's in contact with a pencil because we cannot see it or touch it, you are explaining this phenomenon with black magic. You're saying this happens by magic, with nothing touching it. Nothing coming in contact with it. When you jump and you fall back to earth, why do you fall back to earth? Well, nothing is in contact with me. Yes, something had better be in contact with you. Otherwise, you are explaining your phenomenon, the fact that you jump and you're pulled right back. You're explaining that with black magic. Okay? So before we explain our version, let's give an introduction to it. You have to know what we're trying to figure out here, okay? And this is a very important thing that a professor, his name is Richard Muller, he worked at least at Berkeley, okay? And this is what he had to say about what it is that you have to explain about gravity, okay? Listen carefully, okay? This is not mine. This is someone at Berkeley, professor, right? This is what he says, okay? Here he goes. Listen carefully.
What's the force of gravity on me? It's the pull of the Earth on my body. So, for example, if you have the Earth with its big mass here, and you have you with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. On the other hand, there are a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things.
Okay? Every atom of you, every single atom in your body of you is pulling on every atom of Earth. Every atom of Earth is pulling on every atom of you. Okay? If you say there's nothing there because you cannot see or touch it, you're doing black magic. The only way you can pull on every atom on Earth and for every atom on Earth to pull on you is because there's an invisible, intangible thing, elongated thing that is connected from every atom in your body to every atom on Earth. There is no other explanation for that. And the only reason the mathematicians have not ever come up with that is because they could not see or touch it. But an object is not that which you can see or touch. An object is that which has shape. An elongated object has shape. 3D object, right? It has shape. It doesn't necessarily mean you can see or touch it. Okay, that's the bottom line. That's what prevented this from, or why it took more than 2,000 years to figure this out, because they could not see or touch it, and they said, we're going to resolve this through mathematics. No, you can't, and you can't resolve it through an experiment, because if you cannot see or touch it, you cannot go to the lab and say, I'm going to see or touch whatever is mediating gravity. You can't, because you can't see or touch it. Is that clear? And this is what these people never figured out, because they're trying to do math. They're just saying, well, this is the force of attraction. Yeah, that doesn't tell me what caused it, the mechanism. Okay, that's the issue. Okay, so we got that straight. That's what we have to explain. And here we have it. This is the difference between mathematical physics, that's been done until today. They're talking about discrete particles. That's why they cannot explain anything. That's why they talk about action at a distance. Under the proposal that we have here is we say that all atoms are interconnected. Now you can explain why every atom on Earth pulls on every atom of you, and you pull on it, because every atom in your body is connected to physically connected to every atom on Earth. It's connected via an intangible, invisible entity. We call it the rope, because that's the shape it has, and that's the only reason for that. But it's an elongated, very skinny, very thin object that we cannot see or touch. We pass our hands right through it. Okay, and that's why every atom of you pulls on every atom of Earth. Every atom on Earth pulls on every atom of you, which is what we have to explain. And here we explain it. We're saying every atom in your body is connected to every atom on Earth. We're done. That's how simple it was. No mass, no energy, no field, no force, none of those mathematical words. Just physics. We're saying your atom is attached to the atoms on Earth. Every atom in your body is attached to every atom of me. Okay? And so on. All atoms in the universe are physically interconnected. No action at a distance, no black magic. Once you have the connection, it's easy to understand. It's kid stuff. Okay? And I always give the example, guy brings his 10-year-old son, and they see a farmer pulling on a donkey from a rope, right, tied around the donkey's neck. So as he pulls, the donkey comes towards him. So the man asks his son, how did he get the donkey from point A to point B, closer to the farmer? And the guy says, and the kid says, he pulled on the rope. It's so simple. It's just not even, it's a no-brainer. It's what you saw him pulling on the rope, pulling on the donkey. Now make the rope disappear. And now the farmer goes like that, and the donkey comes towards him. And now the father asks his son, how did the donkey go from point A to point B? And the kid says, I have no clue. I don't know how that happened. Magic. And the only issue is that he can't see the rope. Because if he could see the rope, it was kid stuff. But if you can't see the rope, it's black magic. We'll never answer the question. That's all it is. That's where we're at today. Okay, so here we have our explanation for gravity. Okay, here it is. We call them effective ropes. You have 5 atoms in the cube tied to one atom, number 6, in the cylinder. Okay, we call it one effective rope because essentially it's a pull or a tug between 1 and 6. 2, 3, 4, and 5 don't exist for all practical purposes because they're on the same axis. So they're all pulling on the same line, so to speak. But what happens when they go out of alignment? For example, when the distance between the cylinder and the cube change, cylinder comes closer. Well, now you can see that the atoms are the ropes that connect, or these effective, we call them effective ropes. Now each rope is pulling independently and not on the same axis. And so it's like suddenly you have 5 ropes, okay, instead of 1. Okay, and that's why gravity increases as 2 objects come closer to each other. And there on the upper right, you'll see 2 objects far away. They have all the ropes more or less on the same axis. Lots of them are exactly on the same axis. They superimpose. And again, because there's no see or touch between ropes, okay, they don't touch each other. They superimpose perfectly well, okay? And that's what people have trouble understanding or accepting, okay? But that's an assumption you have to make. And then what happens as the objects come closer together? Well, the ropes fan out, and you can see how gravity is becoming stronger and stronger as the distance between the 2 objects decreases. Okay, so what is Newton's equation? Weight equals gravitational constant g, mass divided by distance squared. Well, what you're talking about is the number of effective ropes. That's what the mass divided by distance square factor represents. It in fact represents the number of effective ropes. Okay, that's our explanation. Okay, and so here we have a comparison, okay, of the 3 proposals. Okay, here's the quantum slash string theory proposal. Okay, you have all these particles coming from the Earth to the Sun, or the Sun to the Earth, and somehow that prevents the Earth from flying out of the solar system. How do you produce that? By throwing particles one way. Okay, so whether the Earth throws particle at the Sun or the Sun at the Earth, it doesn't explain the mechanism. It doesn't explain gravity. It doesn't explain why the Earth doesn't go flying out of the solar system. Okay, so it doesn't. It's an irrational mechanism to introduce particles. Here's the relativity version, which is another one. Okay, here you have the Earth going around space-time. Space-time, the Sun is in the center, blowing or pushing, I guess, the canvas downwards. And so because it pushes it downwards, it creates this depression in time. Okay, so we have warp time. That's what the green stuff represents. And now that you have that green warp time, the Earth that cannot fall out of the solar system, you could say, or fly out. Why? Because its surface is rolling or sliding around that warp time. What sense does that make? None at all whatsoever. So don't tell me you proved it. Tell me what the mechanism is. Tell me how you're going to warp time. What are you warping? The seconds, the minutes? And here's our version, okay, and you can see it here, very easy to understand. The Sun simply twirls the Earth around itself, okay? And why? Because all atoms on Earth are connected to every single atom in the Sun. The Sun simply goes around and twirls the Earth around itself, okay? And that's easy to understand. Now you know why the Earth goes around the Sun. There's no friction between the Earth and space, because space is absolutely nothing, meaning it's that which has no shape. So there is no friction between Earth and space. Earth cannot rub, Gaia cannot rub her shoulder or her elbow against space, because space is absolutely nothing, meaning that which has no shape. There is no ether in there. It's not filled with energy or fields or any of that nonsense. No, all we have is between objects, between atoms, you have these elongated entities. We'll call them ropes. Okay, and that's why celestial objects don't fly out, for example, out of the solar system. They swing around. And then, is there something out there in space? All we have is the crisscrossing of ropes from other atoms in the universe, going right through the Earth and out to other atoms on the other side of the universe. That we have across the entire universe. People say, how many ropes are there? We don't care. There's lots of them. There's lots of atoms in the universe. There's lots of ropes. Very simple stuff. No biggie. Okay. Quantity is not an issue. Okay. So those people who raise quantity issues are simply chasing their tail around.